Hi everyone, and welcome to the first in a series of videos that I'm going to be doing about basic algebraic topology on the subject of homotopy, the fundamental group, and covering spaces. So this roughly corresponds to chapter 1 of Algebraic Topology by Alan Hatcher, which is a good reference text and a nice geometric book to learn algebraic topology from. And I wanted to cover the basics of homotopy before I decide to make more videos on things like homology and cohomology and the relation to differential topology, as well as maybe more advanced homotopy theory in the future. So this set of videos is focused on setting up the basic language of algebraic topology and exploring one of the most fundamental algebraic invariants of path-connected topological spaces, namely the fundamental group. In this video, I want to talk about homotopy of maps, and this is a condition on continuous maps between topological spaces that corresponds to the intuitive notion of deforming one into another. So to start, whenever I write spaces, I'm going to assume they're path-connected. I'm going to assume knowledge of point set topology, and whenever I write a function between topological spaces, I'm going to tacitly assume it's continuous unless I say otherwise. So let f and g be two continuous maps between topological spaces x and y. We want to formalize the notion that there is some continuous deformation of f into g, in which case we call these maps homotopic. So I will define f is homotopic to g if there exists a continuous map. I'm just going to write map and suppress continuity, which is assumed. Capital H for homotopy from the unit interval, which I'll denote by I, this is just 0, 1, with its usual topology in the reals. So it takes in as input something in 0, 1 and a point in x, and it spits out something in y. And the idea is we want to think of this interval as parameterizing some kind of time. So we think of sliding along the interval as controlling some time parameter, where at time 0 we have this map f, and at time 1 we have the map g. So we have this smooth deformation between these, or sorry, continuous deformation. So let's say we have this continuous map such that at time 0, the value at any point x is f of x, right? If we hold some value of I constant, we then get a map between x to y. And at time 1, we get g of x. Okay, so here is an alternate viewpoint on a homotopy. Instead of thinking of this as a map from I times x, we can think of it as a family of maps which I'll call little ht for t in the interval between x and y, such that h0 equals f and h1 equals g. And I'll interchange between these notions freely. So these are either have something from the domain times the interval, you're parameterizing there, or you think of it as a one-parameter continuous family of maps from x to y. All right, let me give an example. This is a fairly standard and easy example. Let me take x equals y, which is just the real line. And suppose I have the identity map and the map x squared. Right? These are both continuous maps. Then I claim that f and g are homotopic. Via this map htx, which is this interpolation between them. So at we initially have this 1 minus t times x. So we just take this convex linear combination of these two maps. And you can see that this kind of thing generalizes a great deal, this convex linear homotopy between these two maps. So now, of course, if we're at time 0, right, then this thing vanishes, this term, and we're just left with 1 minus tx. T is 0, so this is just x. So h of 0, x is just f of x. And similarly, h of 1 comma x is just x squared because this first term, 1 minus t times x, vanishes. And it's easily seen that h is continuous from as a map from the interval times r into r. Great, so we've given an example. Let's generalize this a little bit, this idea of a linear homotopy. Let's take x to be Rm and y to be Rn for m and n non-negative integers, and f and g are going to be any two arbitrary maps x to y. So I claim that these guys are going to be homotopic. And this time I'll use the other definition of homotopy just to get some practice, show you what this might look like. So we have this homotopy, which is just 1 minus t times, sorry, this should be f of x, plus t times g of x. This is always a continuous map from x to y, and it gives you a homotopy, where if you plug in t equals 0, you get f, you plug in t equals 1, you get g. Okay, so one should check that homotopy is an equivalence relation which means that we can kind of unambiguously use this notation that we've been using already. Recall that equivalence relation, you have to just check that it's reflexive. So f is homotopic to f. This is just via the easiest homotopy you can think of. Just take identity homotopy. So then the next thing you have to check is that f being homotopic to g is the same, or is equivalent to g being homotopic to f. Think of a way to reverse the homotopy in time, right? And replace t with 1 minus t, just play things in reverse. And the last is transitivity. So if f is homotopic to g and g is homotopic to h, then f is homotopic to h, right? And the way you want to think of this is if this is given by a homotopy h and this is given by a homotopy h prime, then try to think of a way to split the time in the interval 0, 1 into 0, 1 half and 1 half, 1. In the first half, play h in double time. In the second half, play h prime in double time. So you just speed up the homotopies between each of the individual pairs of maps. Great, so this is homotopy of maps. Now I want to talk about this notion where we say that spaces are homotopy equivalent. So let me introduce this definition. Two spaces x and y are homotopy equivalent if there are maps f from x to y and g from y to x, such that f compose g, which is a map from y to itself, is homotopic to the identity on y, and such that g compose f is homotopic to the identity map on x. And then we are going to write this the same way as we did with homotopy of maps. We indicate that x is homotopic to y, and note that this is also an equivalence relation. So one quick special case of this, which is a condition on a topological space that will be important, we say that x, space x, is contractible if it is homotopy equivalent to a point. And we can think of some nice easy spaces that are homotopy equivalent to a point. So let's think of R2 right? Then I'm going to take any point, I'll just send it to 0. You can think of just like contracting inward. And specifically, right, you have f from, let's say, this is a single point, just 0 to R2, which embeds 0 to the origin. And we have a map from R2 to 0, which just sends any point x comma y to 0. Okay? So now we can very quickly see that G compose F, if we do F and then send that to 0, right, we're just, when we compose these, this is just the identity on X. So this is just the identity. So of course, it's homotopic to itself. And any two maps from R2 to R2 are homotopic by this linear homotopy that we talked about a little bit earlier. So this is the special case where we take m equals n equals 2. So in particular, the composition as a map on R2 is going to be homotopic to the identity, which is also a map on R2. Great. So this establishes a homotopy equivalence between R2 and a point. So R2, by our definition above, is a contractible space. Similarly, we can show, and I won't do this in detail, but it's going to work out. Oh, sorry. Rm and Rn are homotopy equivalent for any m comma n. So this should be interesting. If you've taken topology already, which hopefully you are familiar with before watching these videos, you know that there's already an equivalence relation on topological spaces given by homeomorphism. And this is already an indication that homotopy is a bit weaker than homeomorphism. Homeomorphism is more stringent in this case because Rm and Rn experience invariance of domain, or dimension sometimes it's called, where Euclidean space of different dimension are not homeomorphic. And you can prove not diffeomorphic using straightforward differential topology methods. Not homeomorphic actually requires some algebraic topology. But here we see that Rm to Rn are homotopy equivalent when they are not homeomorphic. So this should already indicate that homeomorphism is stronger than homotopy equivalent. Sometimes if we're trying to classify topological spaces, homeomorphism is too strong and invariant. There's no easy way to tell us that two spaces are homomorphic. So we search for a weaker invariant, which is easier to see or to calculate, and that's why homotopy equivalence is so useful. Okay, let me talk about another special case of homotopy, which is deformation retractions. So first let me talk about what a retraction is. Or let me just do it as a definition, it's like a subsection. Suppose A is a subspace of X, and let iota be the canonical inclusion map as a subspace. So then a map R from X to A is a retraction if R of X equals X for all, yeah, let me change the notation a bit. If R of A equals A for all A in here. So equivalently, if we restrict R as a map to A, this is just the identity. So you want to think of a space and some subspace, and we can think of, like, let's say, squishing all the outer stuff inward, but we don't do anything to the stuff in the blue, right? This remains fixed. It's the identity. Okay, so this is kind of a weak notion. Some people use different stronger conditions, or what they call a retraction. Like, for example, a retraction, the case that we're going to be interested in is if all the stuff goes to A eventually, right? The image of this map is A. That's not necessarily the case in what we define to be a retraction. We could even, expand this purple stuff. We could squish it in some way that doesn't force it into A. But the special case that we're interested in below is called a deformation retraction, which does do this. Okay, so just for one example, a concrete example of a deformation retraction, this map that sent everything in R2 to 0 is a deformation retraction to the origin. Or, sorry, is a retraction to the origin. Now I will talk about this other case that we're interested in for homotopy purposes. A is, again, a subspace of X, and R is a map from X to X with image equal to A. Okay, so then suppose R is a retraction. So I will call, so Hatcher does this a bit differently. I'm going to talk about a slightly different way of going about things and then indicate how this relates to what Hatcher defines. So I will call R a weak deformation retraction if there is a homotopy H sub t from X to X such that H0 is the identity on X, and such that H1 is equal to this retraction, R. Okay, and note that if you have a weak deformation retraction, if R from X to A is a weak deformation retraction, then HT as above yields a homotopy equivalence between X and the subspace A. Okay? So again, we think of it like above. This homotopy brings all the stuff in X, and it's going to be homotopy equivalent to the subspace A. We want to think of it pushing everything into A, right, over time. And moreover, a weak deformation retract is actually strong if, in addition to these two bullet points and notation as above, the restriction of the homotopy to the subspace is the identity map. So not only does the homotopy squish everything into the subspace, it also leaves the subspace unperturbed during this whole time. And this is a stronger condition, obviously, because we're imposing an additional constraint on the homotopy. We do not need a strong, note that we only need a weak deformation retract to ensure a homotopy equivalence between X and a subspace. And to touch on what I briefly mentioned earlier, Hatcher, this is my caution symbol, Hatcher's deformation retraction is going to be our strong deformation retraction. He does not talk about weak deformation retractions, and this is what we'll mean going forward if we suppress either weak or strong, right? If we just say deformation retraction, we're going to assume it's a strong one. Okay. Let me give an example of a strong deformation retract. We are going to let X be the n+1 dimensional unit sphere. Well, this is, well, the n dimensional sphere in y equals, oh wait, this should be Sn. I think this should be Sn, yeah. As a subspace of R n+1. And this is given by the n+1 tuples in Rn+1 such that the sum of these guys' squares, or their norm, is equal to 1. Okay. You know what? Let me say y is Rn+1 minus 0. So claim y deformation retracts onto X. And in R2, we can visualize this as follows. Let me do this in a different color. We are going to send, this is a puncture. We are going to squish everything like this, because we want to send everything to this normalized vector. So let R be defined from Rn+1 minus 0 to Sn as above, and we want to send each y to the normalized vector where we divide out by the norm of y. And this certainly gives us something on Sn. Okay, so this is a retraction because we want to check that if y has unit length, then it gets sent to itself. That is, this subspace Sn gets preserved, it gets fixed under this homotopy. And this is true because, not under this homotopy, let's say, but under this map that normalizes each vector. This is true because if the norm of this guy is equal to 1, then y gets mapped via the retraction to y over its norm, which is just y because this denominator is 1. So it gets fixed under R. Okay, And now we have this retraction. So what is the homotopy given by? So the homotopy I'll again give it in the form that is a parameterized family of maps. Let's say ht of y is going to equal 1 minus t minus t over norm of y times y. And one can check that this in fact gives this linear interpolation as we talked about before. Okay, so the overarching idea of what we've done, we want to introduce this notion of homotopy equivalence. Is a weaker form of classifying than homomorphism, and this is, I'll call this bullet point 1, and 2 is that under our setup, homotopy equivalent spaces will have many of the same algebraic invariants that we're going to introduce. That is pi1 of x, which is the fundamental group, the homology groups Hn, and the cohomology groups H over n. So these algebraic invariants are going to tell us when two spaces are distinct, right? If these algebraic invariants are different for two different spaces x and y, then x and y cannot be homotopy equivalent. And in particular, they can't be homeomorphic, or if they have some smooth structure, they can't be diffeomorphic. So this whole motivation comes from the naive desire to classify topological spaces, and our discussion of homotopy of maps and homotopy equivalence of spaces, then giving examples of such homotopies and deformation attractions is a first step in doing so. So thanks for watching this video, and I hope to see you in the next one.